Hello friends, and welcome to our video lecture on topic R3.2 Electron Transfer Reactions. Here we're going to look at a little bit of an introduction to reduction and oxidation. We're going to talk about half reactions and the activity series. Our guiding question: what happens when electrons are transferred? Our understandings are here if you want to pause the video and read them. Please do know that there are other understandings in this topic. We're going to save a few for our video on electrochemical cells. We're going to save another few for our unit on organic chemistry. Our objectives for today: we're going to define oxidation and reduction. We're going to look at reactions and figure out which species was oxidized and which was reduced in those reactions. We're also going to identify oxidizing agents and reducing agents in those reactions. We're going to assign oxidation states to species, particles, in all kinds of formulae. We're going to write some half reactions, and then we're going to wrap up with a look at the activity series, which just tells us the relative ease with which halogens can be reduced and metals can be oxidized. There are lots of ways to describe and define oxidation and reduction. Originally, oxidation was just the gaining of oxygen. Magnesium here is being bound to oxygen in this combustion reaction. It is now magnesium oxide. It's been oxidized. We can also talk about oxidation and reduction in terms of loss and gain of hydrogen. The loss of hydrogen is oxidation, the gaining is reduction. Here we have the molecule ethene. It is gaining some hydrogen. It has been reduced to ethane. We also talk a lot about electron transfer in terms of oxidation and reduction. Here we have the atom sodium. It has that one valence electron. Chlorine is in its elemental state. It has not yet gained any electrons, but we know that that valence electron can be transferred from the metal to the nonmetal. We would say that the sodium has been oxidized because losing electrons is oxidation. The chlorine here has been reduced because gaining electrons is reduction. We can also talk about the change in oxidation state when we're looking at oxidation and reduction reactions. Here we have elemental hydrogen. Its oxidation state is neutral or zero. Same thing for this elemental oxygen. However, and this is a little quirky, we're going to talk about this in a couple slides. In this molecule, we're going to give oxygen a -2 oxidation state. That does not mean that it has a -2 charge, but it's more electronegative than hydrogen, and so it's partially -2, so we just kind of round up and give it a -2, not charge, but oxidation state. And then hydrogen, because oxygen is pulling those electrons away a little bit, we're going to give hydrogen a +1 oxidation state. Notice that hydrogen's oxidation state has changed, as has oxygen's oxidation state. Because oxygen's oxidation state went down, it was reduced. And then hydrogen's went up, it was oxidized. A decrease in oxidation state is reduction. I previewed this mnemonic device on the previous slide. Losing electrons is oxidation, gaining electrons is reduction. But this really only gives us help with one of our descriptions of oxidation and reduction. So this one might be more inclusive. Oxidation is losing and reduction is gaining. Let's see if we can figure out, using our mnemonic devices in these descriptions, to determine what was oxidized and what was reduced in this reaction. Did anything lose oxygen? Well, here this potassium and chlorine have 3 oxygens, and here they have none. That is a loss of oxygen. That's reduction. Did anything gain oxygen? Well, here potassium and chlorine have 3 oxygens, and here they have 4. This was a gaining of oxygen. This was oxidation. Can a single compound, a single species in a reaction, both be oxidized and reduced at the same time? Yes. Yes, it clearly can be. We have a vocab word for that, and that word is disproportionation. Disproportionation. Disproportionation, when we have a single species both oxidized and reduced at the same time. Let's practice assigning some oxidation states to identify oxidation and reduction. So here I have calcium. It is the element calcium, and it has not yet lost any electrons. We're going to give it an oxidation state of 0 because it's neutral. Same thing for this oxygen. It has not yet gained any electrons. It's still neutral. It is going to have an oxidation state of 0. Here we know that electrons are being transferred from the calcium to the oxygen. Calcium has 2 valence electrons. Those are both going to get transferred to oxygen. That's going to give calcium an oxidation state of +2. When those oxygen atoms gain those electrons, it's going to have an oxidation state of -2. We have these oxidation states written on our periodic tables. Alkaline earth metals are +2s, oxygen's a -2. Notice that we had a change in oxidation state. Calcium went from 0 to +2 because it lost electrons. Losing electrons is oxidation. Which species was oxidized? The calcium was oxidized. Which species was reduced? Who gained those electrons? Well, oxygen went from 0 to -2. It got extra negative because it gained those extra 2 electrons. Oxygen was reduced. We can also talk about what caused calcium to be oxidized. Because oxygen took electrons away from calcium, we can call oxygen the oxidizing agent. Oxygen caused calcium to be oxidized, therefore oxygen is the oxidizing agent. Because calcium gave electrons to oxygen, causing it to be reduced, we can say that calcium is the reducing agent. By being oxidized, giving electrons away, it caused something else, that oxygen, to be reduced. So it is the agent of reduction. Kind of quirky vocab. The thing that is oxidized is the reducing agent. The thing that is reduced is the oxidizing agent. We're going to need to assign lots of oxidation states to species in reactions in order to figure out when reduction and oxidation are occurring. So here we're just going to look at some rules for assigning oxidation states. Free elements are always going to have oxidation states of 0. This oxygen that is bound to only oxygen is going to have an oxidation state of 0. It's neutral. It's not yet gained or lost electrons. Groups 1 and 2 are going to always be +1 and +2, with the exception of hydrogen. We'll talk about it in this bullet point. Our alkali metals are always going to have those oxidation states of +1. Alkaline earth metals are always going to have oxidation states of +2. Aluminum is going to have oxidation state of +3. Hydrogen is going to be a +1 when bonded to a non-metal. Here we've got the non-metal chlorine. It has an oxidation state of -1. Hydrogen is going to have a +1. You might be thinking, wait. This is a covalent bond. We didn't transfer electrons. This is true. However, due to electronegativity differences, chlorine does have a partially negative charge. We're going to just kind of round that up to totally -1. But this is not actually a charge, it's an oxidation state. So be careful. Here, now that hydrogen is bonded to a metal, we're going to give hydrogen the -1, and sodium is going to be the +1. Notice that most of the time, not all the time, but most of the time, our negatively charged species is going to be more to the right in our formula. The positively charged species is going to be more to the left in our formula. There are exceptions, so this is not always, but this is often. Oxygen is -2 most of the time, almost always. When it's in a peroxide, H2O2, it's actually only a -1. So here we have 2 hydrogens that are each +1. These 2 oxygens are each -1. That's going to balance out that molecule to a neutral 0. Also, oxygen, if it's bound to fluorine, might not be -2. Because fluorine is more electronegative than is the oxygen, we're actually going to give a -1 to fluorine. Oxygen gets a +2. What? Mind's blown. Does this mean that fluorine stole electrons away from oxygen? No. They're still sharing. It's just that because fluorine's more electronegative, we're going to give fluorine the negative oxidation state, not a charge, but an oxidation state. Therefore, fluorine gets the -1, oxygen ends up with a +2. Whack-a-doodle, right? Other halogens are going to be -1 in binary compounds. We looked at the hydrochloric acid on the previous slide. Chlorine gets that -1, hydrogen is going to get the +1. But wait, sometimes if we're combined with oxygen, halogens, with the exception of fluorine, because it's always -1, can be positive. So here, my oxygen is going to get the -2. The hydrogen is going to get a +1. I have 4 oxygens. -2 times 4 is -8. Right now, I have -8 on this end. I have a +1 on this end. What do I need to put in the middle to balance this whole molecule out to a neutral 0? +1 and -8. I'm going to make this chlorine a +7 in order for the whole species to have a neutral charge. +1 + 7 - 8 balances out to 0. Does that mean that chlorine gave away 7 electrons? It does not. It just means that relative to the oxygen, it's a little bit less electronegative, and so therefore we're going to round way up. Chlorine isn't actually a +7 charge, but we're going to give it a +7 oxidation state. I do find that with molecules like this, it is easiest if we start to the far right. It's going to be the most negative most of the time. And then go to the far left. That's going to be our positive oxidation state. And then you can figure out what needs to be in the middle. Finally, our transition metals are going to have Roman numerals to tell us their oxidation states. This iron has an oxidation state of +3. Do be careful about oxidation states. Oxidation states always are going to have the charge in front of them. I know they're not exactly charged, sign. I should call it a sign, not a charge. We're always going to put the sign in front of the number. Sometimes when I'm writing that calcium is an ion, that sign comes after the number. For oxidation states, it's always before. So be super careful. This, yes, for charge. This, yes, for oxidation state. Sometimes we can also use those Roman numerals, so I could say oxidation state of 3. Let's practice assigning some more oxidation states. I really like to start by going to the far right of a formula. Oxygen here is going to be a -2. -2 times 4 of them is a total -8 coming from all of the oxygens. Manganese, in order to balance out that -8, is going to have to be +8. So the oxidation state of manganese is +8. The oxidation state of oxygen is -2. When we state the oxidation states, it's of each individual atom, not the combined. Let's look at CO2. Again, starting on the right, oxygen's a -2. -2 times 2 is -4. What does carbon have to be to balance out that -4? It's going to have an oxidation state of +4. +4 and -2 are the oxidation states of the 2 elements in this particular species. How about copper 1 nitrite? Again, starting on the far right, oxygen is going to be a -2. -2 times 2 is -4. This guy has several atoms, so now I'm going to go all the way to the left. I know that nitrite has a total charge of -1, which means that copper is going to have to be +1. So I have +1, -2, total -4 though. -4 and +1, what does nitrogen have to be to balance that out? It's going to be a +3. +1, +3, -4 balances out to that neutral charge of 0. So my nitrogen's oxidation state is +3. Does that mean that it lost 3 electrons? It does not. Its charge is not +3. Its oxidation state is +3. One more. Let's look at ethanol. This is one of those exceptions where my far right is not going to be negative. This hydrogen, not a -1. This oxygen, however, is definitely going to be a -2. My hydrogens, because they're bound to nonmetals, oxygen and carbon are nonmetals, I'm going to give all of these hydrogens positive ones. So my total hydrogen positiveness is going to be 5 times 1 plus 1 times 1. I have a positive 6. Oxygen's negative 2. What does the total charge of the carbons need to be to balance this out? Positive 6, negative 2. I need a negative 4 total, but I have 2 carbons to make that negative 4. That means that each carbon's oxidation state needs to be negative 2. Negative 2 times 2 gives me negative 4. 5 plus 1 times positive 1 gives me positive 6. Oxygen's 1 times negative 2 is negative 2. Negative 4, negative 2, and positive 6 balance out to 0. So again, carbon's oxidation state is each of them by themselves negative 2. Hydrogen, each of them by itself is a positive 1, and oxygen's a negative 2. Let's practice in a formula. So my hydrogen here, super easy. It's elemental. It's going to have an oxidation state of 0. It has neither gained or lost any electrons yet. Here, hydrogen is bound to a nonmetal. That means hydrogen is going to get a positive 1. This is another one of those exceptions where we put the positive on the right side, even most of the time the negative's on the right side. I have 4 of these hydrogens that are each positive 1, which means that my total charge on the right is positive 4. I need to have a negative 4 on the left to balance that out. I have 2 carbons that are going to add up to negative 2. That means that each carbon has to be a negative 2. So my oxidation states are negative 2, positive 1, and 0 in my reactants. How about over here? Now I have 6 hydrogens that are each going to have a positive 1 oxidation state. That's a total of positive 6, which means that my carbons need to add up to a negative 6. In order to do that, these 2 carbons need to each be negative 3. Negative 3 times 2 gives us that negative 6. Notice that our carbon went from a negative 2 down to a negative 3. That means that carbon was reduced. We would actually say this whole entire molecule, the species, was reduced. What was oxidized? This hydrogen. Its oxidation state went from 0 up to positive 1. That means that it was oxidized. Let's practice another one. This is the polyatomic ion oxalate. We're going to start on the right this time, not an exception. We're going to give our oxygens negative 2. So negative 2 times 4 is negative 8. Carbon needs to be a positive 8. Is that right? No, because look, the whole oxalate polyatomic ion has a charge of negative 2, which means that I don't want to balance out to 0, but instead I want to balance out to negative 2, which means I'm not going to give these carbons positive 8 total charges, but instead positive 6, because positive 6 and negative 8 adds up to negative 2. If the total carbon oxidation states added up together are positive 6, and I've got 2 of those carbons, each of them is going to be a positive 3. Let's look at this next one. My oxygen is going to be negative 2. Negative 2 times 4 is negative 8. Should manganese be positive 8? No, because look, again, I've got another charge. So this total thing needs to add up to a charge of negative 1. I've got negative 8. My manganese needs to add up to a positive 7. Positive 7 and negative 8 adds up to negative 1, which means that my manganese oxidation state is going to be a positive 7. On the other side, now I've got some oxygen. It's going to be negative 2. Negative 2 times 2 is negative 4. This has no charge, and so I'm going to give that carbon a positive 4 oxidation state, positive 4 and negative 2. Manganese all by itself, well, it's not an element because clearly we've got a charge right there, which means that its oxidation state is also positive 2. Let's figure out what was oxidized and what was reduced. Carbon went from positive 3 to positive 4. Its oxidation state was not reduced. It didn't go down. It went up. That means that it was oxidized. It was not reduced. It was oxidized because that oxidation state went higher. What went down? Manganese went down. Manganese went from 7 all the way down to +2. It was reduced. That oxidation state went down, it was reduced. So this oxalate polyatomic ion was oxidized, this polyatomic ion was reduced. What was our reducing agent? Remember that the reducing agent is the thing that caused reduction to happen. The reducing agent makes something be reduced. What made that guy be reduced? Well, it was the other guy. This one is our reducing agent. What's our oxidizing agent? Remember that the oxidizing agent is the thing that causes something to be oxidized. Because this oxalate polyatomic ion was oxidized, because this one was reduced, this MnO4-1 polyatomic ion is our oxidizing agent because it caused this one to be oxidized. This one is our reducing agent because it caused the other guy to be reduced. This reaction, a little bit easier. Sodium as an element is going to be neutral. It has an oxidation state of 0. Chlorine also is elemental. It is not yet gaining any extra electrons. It's only sharing with other chlorines. It's going to be neutral. It's going to have an oxidation state of 0. Here we know that chlorine is going to have an oxidation state of -1 and sodium is going to have an oxidation state of +1. What was oxidized? What lost electrons? Notice that sodium went to a +1 charge. It was oxidized. It lost electrons. Chlorine here was reduced. It gained electrons. Sometimes we like to show just what was oxidized all by itself. We don't want to show what was reduced. And so we write what we call half reactions. We can write the oxidation half reaction showing just what was oxidized. That oxidation can be the loss of electrons. So I'm going to take my 2 sodiums that turned into 2 sodium ions, and what did they lose? Those 2 electrons. So this is going to be my oxidation half reaction. 2 sodium atoms become 2 sodium ions, and those 2 electrons that were lost. Let's go ahead and draw our reduction half reaction. Remember that gaining electrons is reduction. So our reduction half reaction is going to be just what was reduced. What was reduced? Well, we decided that chlorine was reduced. So I'm going to start with my chlorine. What happened to the chlorine? It gained 2 electrons, and then we had 2 chloride anions. Notice that these 2 electrons are a match for those 2 electrons. The difference is that those electrons are produced and released. Those electrons are added. Another example, let's identify our species that have been oxidized, that have been reduced, and we'll write some half reactions. Iron here is elemental. It's all by itself as an element. It's going to have an oxidation state of 0. Here, my chlorine is going to be a -1. Silver is going to be a +1. Here, now my silver is elemental. It is an element all by itself. Its oxidation state is now 0. Chlorine is still a -3. There are 3 of them, which means that my iron has to have an oxidation state of +3. Let's figure out what was oxidized, what lost electrons. Well, iron went from neutral with all of its electrons all the way up to an oxidation state of +3 because it lost 3 electrons. And so therefore iron has been oxidized. What was reduced? Well, our silver went from a +1 down to a 0. It was reduced because it gained electrons. Here it had lost an electron. Here it got it back. So it gained that 1 electron to go back to neutral. What about chlorine? Was chlorine oxidized or reduced? Neither. Its charge didn't change. And so we say that chloride is going to be one of our spectator ions. Spectator ions are species in reactions that don't have a change in oxidation state. To write our oxidation half reaction, what was oxidized? It was that iron. So we're going to start with iron. we're going to convert that iron into iron with a +3 charge. And then we also have released from that iron atom those 3 electrons. Our reduction half reaction, what was reduced? We decided that our silver was reduced. So we started with 3 silver cations. Each of them gained 1 electron, but I need 3 total for those 3 ions. And that gave us those 3 atoms of silver that are now neutrally charged. Notice again that my electrons match. I have 3, I have 3. These were released, these were gained. We give the halogens a -1 oxidation state on the periodic table because we know that these guys are going to have oxidation states of -1. They're going to gain electrons, but they don't all gain electrons as easily as each other. And so we can talk about this relative ease of reduction, which is related to what we call the reactivity series or the activity series of halogens. The activity series of halogens follows the periodic table. The higher we are up in group 17, the more likely you are to be reduced. More easily reduced, less easily reduced. So if I'm combining fluorine gas with sodium chloride, we're going to produce some chlorine gas and 2 of them, sodium fluorides. Because fluorine is more easily reduced, is more reactive than is chlorine, because it's higher up on the periodic table. Fluorine absolutely is going to knock that chlorine off of the sodium and take its place, leaving chlorine to be elemental. What has happened here is that fluorine went from a 0 to a -1. It was reduced because fluorine's really good at being reduced. Our chlorine went from a -1 to a 0 because now it's elemental. Chlorine was oxidized, and usually we don't think about halogens as being oxidized, but in this case it was because fluorine is higher up on the activity series. It is more easily reduced. What if I combined bromine with sodium chloride? There's my bromine. Can bromine, which is lower on the periodic table than is chlorine, can bromine knock off that chlorine and be reduced to sodium bromide? It cannot. We're going to have no reaction occur here because that chlorine is not going to be oxidized by bromine. Chlorine is more likely to be reduced than is bromine. It's higher up on the periodic table, which means that bromine is not reducible enough to knock that chlorine off of the sodium. Chlorine is going to keep that -1 charge. It's going to leave bromine to stay 0. And wouldn't it be lovely if our metals followed the same rule? So when we look at the alkali metals, so our group 1 metals, excluding hydrogen because it's not a metal, as we go down the periodic table, things get more reactive. And so we would like to say that, well, this guy is going to be more easily oxidized than that one. This will be more easily oxidized than that one, except that's not the whole story. In fact, lithium, which is the least reactive of our alkali metals, is in fact the most easily oxidized of all the metals, not just the alkali metals. So when we're looking at metals in their activity series, we're going to go to our data booklets, table 19. The higher up, the more negative are these reduction potentials, the more likely are these metals to be oxidized. The further down, the more likely they are to be reduced instead of oxidized. So if I'm looking at lithium and sodium chloride, I'm going to find lithium. I'm going to find sodium. Notice that lithium is higher. That means that lithium absolutely is going to be oxidized. And so we're going to make lithium chloride. Lithium is going to go from the 0 to the +1. It's going to be oxidized. That means that the sodium is going to be reduced. Lithium is higher on this standard reduction potential list than is sodium, even though sodium is more reactive than lithium in other terms. How about if I flip that? Can sodium knock the lithium off of the chlorine and take its place? No, because sodium is lower on this table 19. Its reduction potential is a little closer to 0, which means that it cannot be oxidized over lithium. Lithium's going to stay a -1, sodium's going to keep its electron. No reaction is going to occur. Magnesium and hydrochloric acid. I don't have two metals here. I've got this H. Metals react with acids, do some pretty cool things. We also, notice, have thrown hydrogen into our standard reduction potential list. Hydrogen's here. Where's magnesium? Magnesium's way up here. That means that magnesium can, in fact, replace the hydrogen. It's easier to oxidize magnesium than it is to oxidize the hydrogen, which means that magnesium is going to go from the 0 to the +2. It's going to be oxidized as we make magnesium chloride. And then the hydrogen, which was a +1, is going to be reduced to that 0 oxidation state. Because magnesium is higher in this reduction potential list, it is more likely to be oxidized, less likely to be reduced. What about copper and hydrogen fluoride? Ooh, that's a pretty strong acid. I bet that it's going to do all kinds of super cool things to this metal copper. I didn't include the whole entire list of table 19. Copper is actually down here. What? I know. Notice that hydrogen is higher than copper on this list. You know what that means? That means that hydrogen cannot be replaced by the copper. Copper cannot knock hydrogen off because copper actually has a positive reduction potential. It's more likely to be reduced than it is to be oxidized. Crazy sauce. What does that mean? No reaction is going to occur. And in lab, we can actually deduce this idea of relative reactivity. What's more likely to be reduced? What's more likely to be oxidized by combining metals with ions? So when I react, or try to react, silver metal, so Ag that is neutral because it's still the metal, with magnesium chloride is going to be Mg2+. Can I get the silver to turn into silver plus and get the magnesium to turn into magnesium? No. I know it's kind of hard to see in the picture. There's a lot of glare in the lab, but the magnesium didn't do anything to the silver. And here also, silver didn't do anything. Here, it did a tiny little bit. We've got a little bit of greenish from that copper, but the silver didn't actually react, nor did it react in the lead, nor in the aluminum, and not even in hydrochloric acid. You know what that means about silver? It's not very reactive. So it has a very low ease of oxidation. It's more likely to be reduced. Let's look at this magnesium guy. Oh my gosh, look at all that. And there was stuff, and here's more stuff, and here's more stuff. And again, I know that the glare is really hard to see, but we have some mushy stuff in here, and there were oh so many bubbles with the hydrochloric acid. That's because magnesium has a very high ease of oxidation. It is very little likely to be reduced. In the silver, what happened was the silver nitrate, silver had that +1 charge. Magnesium went from magnesium 0 absolutely to magnesium 2+, and silver went from +1 to 0. So I took magnesium metal, and instead of having magnesium metal, now I have magnesium ions. And where I used to have silver ions, now we have solid silver metal, which tells us that magnesium is more easily oxidized than is silver. And on that note, my friends, I hope we're feeling pretty confident about adding the guiding question, what happens when electrons are transferred? Oxidation states change. We've got some reduction oxidation reactions happening. Oxidation is the loss of all kinds of things. Reduction is the gaining of all kinds of things. We talked about how to find out in a reaction what has been oxidized, what's been reduced. I think the easiest thing to do is to identify some oxidation states. Figure out what oxidation states were increased, that's oxidation. What oxidation states went down, that's reduction. We talked about oxidizing agents. These are the things that were reduced because they make something else be oxidized. Reducing agent are the things that were oxidized because they made something else be reduced. We practiced assigning oxidation states to lots of different formulae. We wrote those half reactions where we focused just on what was oxidized. We focused just what was reduced. And then we talked about our activity series, the ease of reduction of halogens. We're just going to use the periodic table, group 17. The higher up they are, the more easily reduced they are. Relative ease of oxidation of metals is a little bit trickier. We're going to look at table 19 in our data booklets. Great work today, my friends.